Today we'll discuss combination of capacitors. Now before we start combination of capacitors, you must have done combination of resistances in class 10. And there we had a series combination of the resistances and parallel combination of resistances. Now in series combination, it is said that if the current through all the resistances are same and potential differences are different across the resistors, then they are in series combination. Whereas for parallel combination, it is said if the potential difference across the different resistances are same and the current through the resistances are different, then they are in parallel combination. So if you use this concept for capacitors, obviously you will say if the charge through all the capacitors are same and the potential difference are different, then they are in series combination. And if the potential difference across the capacitors is same and the charges through the capacitors are different, then they are in parallel combination. So let's use this one, whatever concept you have done. Suppose we have got two capacitors connected to a 30 volt supply. These are two identical capacitors. So potential difference across each will be 15 volt. If we use, suppose, three identical capacitors, then this will become 10 volt each. Whereas for the other case, if I have two capacitors and suppose it draws 30 coulomb of charge. Through each capacitor, charge will be how much? 15 coulomb. If I have three capacitors joined here, then it will become 10 coulomb. Now, if you use your concept that if the charge through all the capacitors are same, then they are in series. So here we have the same value of the charge through the capacitors. So with that, it should be in series. We say that if the potential difference across the capacitors are same, then they are in parallel. Here you can see that it is the same potential difference. When we have used 3, when we have used 2, then it was 15 volt. Again, it was same for both. So with that concept, you will say that this is in parallel. But you know that this is basically in series combination. This is in parallel combination. So what we should try to use for identification, basically you should say if the same charge is flowing through all the capacitors, then they are in series. Now here you can see it is not the same charge which is going through first capacitor and second and third. These are the different charges flowing through the capacitor. So obviously it is not in series. Here you can see whatever charge we take which is flowing through these capacitors, it will be same charge which will flow through first capacitor, second capacitor and third. So they are in series. Similarly, if we say that it is the same potential difference not in magnitude, it is the difference of potential of 2 points which are having the same value. Like here, if I take it may be that it is at 30 volt, this is at 20, this is at 10, so that you get 10 volt. Here also difference you are getting 10 volt, but this 10 volt potential difference we get as the difference of potential of 30 and 20. It is your 20 and 10 giving you 10. It is your 10 and 0 giving you 10 volt. So obviously, this what we say, that same potential difference, it is not the magnitude, but the potential difference what we get, it should be from 2 points having their same values. Like here, if I take whatever is the potential at this point, it is same for all these. Whatever is the potential at this point, it is same, so that it gives the same potential difference and they are in parallel, not here. So we'll use this as the basic statement for deciding the capacitors are in series or in parallel. So now let's use this one for series and parallel combination of capacitors. Now let's take series combination of capacitors. Here we have a C1, C2, C3, three capacitors joined in series, and it is connected to a potential difference V, V1, V2, V3. These are the potential difference across the capacitors respectively. And Q is the charge drawn from the source. So obviously it will be the same charge Q flowing through all the capacitors there. So here you can see that the potential V, potential difference V across this combination, this will be V1 plus V2 plus V3. V1 plus V2 plus V3. V1 we can write Q1 Q by C1, V2 Q by C2, Q by C3. So obviously V can be written as your Q into 1 by C1 plus 1 by C2 plus 1 by C3 as the first equation. Suppose C is the equivalent capacitance. For this entire network, if I am using C to represent the capacitance of the equivalent circuit, so this is the equivalent capacitance of the network there. So V can be written as your Q by C, as that will be represented by equation 2. Now if you equate equation 1 and 2, you will find it will be 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. This is the expression for equivalent capacitance relation for the individual capacitors, okay, which are joined in series. Now let's do for parallel combination. Now let's take for the parallel combination. Here we have taken three capacitors having capacitances C1, C2, C3 connected in parallel across a potential difference V. Let's suppose that Q is the charge drawn from the source, and Q1, Q2, Q3, these are the charge on the individual capacitors respectively. So obviously we can write Q equals to Q1 plus Q2 plus Q3, and Q1 can be written as C1V, Q2 C2V, similarly it is C3V. So Q is equals to C1 plus C2 plus C3V. Let it be equation 1. And if I again we use suppose C as the equivalent capacitance of the network, so we can write Q equals to CV. Let it be equation 2. And if we now compare equation 1 and equation 2, we can write C equals to C1 plus C2 plus C3. So this is for parallel combination of capacitors. You just remember one thing, that the equivalent capacitance formula, what we are getting for capacitors joined in series or in parallel, is just reverse what we get for resistances in series and parallel. So let's take this one. For series combination of capacitors, our formula is 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. Whereas for resistors, for series combination, R is your R1 plus R2 plus R3. Whereas in parallel combination for capacitors, C is C1 plus C2 plus C3. Whereas for resistors, it is 1 by R equals to 1 by R1 plus 1 by R2 plus 1 by R3. Okay, so it is just reverse, you can say. What we get for series for capacitors, the similar formula is there for resistances in parallel. For capacitors, whatever is there for parallel is for series combination of resistances. So this is all about the combination of the capacitors joined in series and parallel. Now, let's do expression for energy stored in a charged capacitor. Energy stored in a charged capacitor. Suppose C is the capacitance of a capacitor which is being charged. This is the source which it is connected, and let Q be the charge on the capacitor at any moment. So we can write Q equals to C into V. V is the potential difference across the plates of capacitor at that particular moment when we have the charge Q there. So Q is equals to CV. Remember, this V is not this particular V across which it is connected. This is the potential difference of the source which is charging this capacitor. So V is the potential difference across the capacitor at the moment when the charge Q is there on the plates of capacitor. So V is equals to Q by C. So small work done will be your V into dQ if dQ is the amount of charge which is further transferred to the capacitor. So it is your Q by C into dQ. If you want to find out the total amount of charge when total amount of work done when the charge Q is transferred to the capacitor or it is given to the capacitor, so it will be the integral of this small work done. So it is Q by C dQ. Integration will be from 0 to capital Q. So it is your 1 by C Q square by 2, which is Q by 0 to Q, or it is your half Q square by C. This is the expression for work done, Q square by 2C. Now, other expression, you know that energy stored in a system is equal to whatever work is being done on the system. So, energy stored will be equals to work done, which is your Q square by 2C. Also, as you know that Q is equals to CV, so we can give different forms of the energy stored as CV whole square by 2C or half CV square, or other expression may be your half Q square by C can be written as half Q into Q by C, or which is your half QP. So the different expressions for energy stored is your Q square by 2C or half CV square or half QP. So these are different expressions for energy stored in a charged capacitor. Let's now do energy density of a charged capacitor. So energy density will be energy stored per unit volume. Volume will be the gap between the plates of capacitor. If it is D and plate area is A, so that volume can be written as your A into D, and this is your half CV square, which is the energy stored. So it is your half epsilon naught A by D for C, and for V we can write ED square. Now how we are writing this? As you know that E is minus del V by del R, so it is your V by D, which is V is the potential difference and D is the separation there. So V can be written as your E into D. So if you take that one and cancel the terms there, you will get half epsilon naught E square. Or finally, expression for energy density will be your half epsilon naught E square. Okay. So this is the expression for energy density of a charged capacitor. So this is all in the capacitors chapter. That is the basic things which is required there. Okay. Thank you.